Welcome to the first of a series of screencasts that will discuss group theory. Group theory is a pleasing and extensive set of mathematical knowledge, and group theory as a discipline underlies a whole raft of mathematical theory and physical theory. Group theory is important for cryptography, it's important in physics, it's important in chemistry, it's important in crystallography. You find applications of group theory all over the place. And so, without further ado, I'm going to define a group. So what is a group? Well, a group is two things. It's an ordered pair of a set G and an operation which for the moment I'll just write as a star, although we'll see that there are other notations. This here is a set, can be finite, or infinite. We'll see examples of both when I start talking about infinite, when we start talking about this. And this is an operation. There are different formal ways to define it, but basically the idea is that if x and y are members of this ground set G here, then x star y is also a member of G. So we've taken xy and we've mapped it to the product. You see different notations. Sometimes you just see xy. It's the same thing, it's just that you denote the product by just writing the numbers next to each other. Sometimes you see it as a little circle like this in some older textbooks, and sometimes you see a dot, but they're all the same thing. So formally what we've got is star, or whatever notation you want, is a map which maps G cross G to G. So x and y being in the group means that the product of the two, or the result of applying the operation, is also in G. You can't escape G by using this product, and this is called closure. Sometimes it's classified as an axiom, sometimes not. There is no requirement, and again I'm going to make this very clear with examples, that xy equals yx. There's no requirement. Sometimes it is. If so, that is, if xy equals yx for all x and y in the group, this notation here, this upside down A, is part of the set quantifier notation, which is covered in an earlier screencast. If this is the case for xy equals yx, then you call it then the group. Then we say that the operation is abelian, after a mathematician called Abel who worked with these things. Okay, so there's no requirement that it does that, and sometimes you say if xy equals yx, you talk about a commutative operation. Commutative, because they commute, because x and y commute past one another. Different notation there. Okay, so we've got an operation, and we're going to. That's not really enough to get going. There's not enough here to say anything intelligent about anything from that. So we need to place some restrictions. So the first restriction is identity, and this is an axiom. Oops, I'll have to charge that up in a minute. So there exists E in the group such that for all x in the group, xe equals ex equals x. You'll see that I'm implicitly acknowledging that that this operation might not commute past, that the operation might not be commutative, simply because I've got to write both of them down. We'll see later that this is a tiny bit redundant, but we'll start with this. So this is like, so E is like, in scare quotes, multiplying by 1. Multiplying by 1, because of course x times 1 equals 1 times x, which equals x. So there's a nice example, or indeed adding 0, because of course x plus 0 equals 0 plus x equals x. Okay, so there's an identity element that's basically a do-nothing. It's sort of a do-nothing thing. Do-nothing. because if I've just done x and then I do something else, that's the same as just x on its own. Okay, so that's the identity. We've also got, or sometimes you call this a neutral element. Different notations you see in different books. Now inverse. For all x in the group, there exists x dash. We'll see different notations for this as well, but for the moment I'm just going to call it x dash, which is also in the group, such that x dash equals x dash x equals e. So we can see that x times x dash equals e. So doing x and then x dash, this thing called x dash, is the same as doing nothing. So x dash is like an inverse to x. So it's like multiplying by 1 over x, because of course x times 1 over x equals 1, and multiplying by 1 is your identity. Or it's like adding 0. No, it's not. It's like adding minus x to get 0. Because of course x plus minus x equals x minus x equals 0. And if you're working with addition, then 0 is your neutral element, your identity element. This is a longer screencast than most, but I think it's important to put all three of the axioms here. There's a final one called associativity. And that says this. That says that for all x, y and z in the group, x, y, z equals x, y, z. And I've spent a long time in my research thinking about associative operations and how to classify them and how to think about them. Associativity is very much a wolf in sheep's clothing. Actually, I say to myself, it's much more like a killer whale in jellyfish clothing, really. It's a very, very simple to state axiom, but very, very profound. There's a lot going on here. Of course, this is true for multiplication of numbers and addition. Well, let's write it out for addition. X plus y plus z. This is an example of an associative operation. That equals x plus y plus z. I hardly even need to state that for addition, but in mathematics you really have to state all your assumptions very, very clearly, or the whole system comes tumbling down. That's true, and we require that our operation has this property here. So if I write it in circle notation, I'm saying x circle y circle z equals x circle y little circle z. This is weird when you think about it. It's very powerful. It's a very, very profound restriction on a binary operation, and I'm just going to give you a taster for how I think about it in my research. Instead of x circle y, I'm going to write some function of x comma y, and I'm going to rewrite the associativity rule in functional notation. So what does that say? So we've got x, y, z equals x, y, z. So that says that f of x comma y comma z. Why is that? Because this bit here is equal to the product here, and this bit here, this overall bit here is the whole thing, because we've operated with z, equals f of x comma f of y comma z. And the longer you stare at this equation, the more confusing it gets. Comma y comma z. All it is the associativity rule, but written in a slightly less amenable notation. And I'm going to put a question mark by that, because the more you think about it, the more confusing it gets. Why on earth should these two things be equal? So just to summarise, we've got a group is an ordered pair for set G and an operation circle or star, whatever. The circle maps G cross G to G, so it's closed because you can't escape G. There exists E in the group such that XE equals EX equals X. That's your identity or neutral. for all x in the group, there exists x dash in the group such that x dash equals x dash x equals your identity. This is an inverse. And for all x, y, z in the group, if you get any three elements in the group, then x, y, z equals x, y, z associative. So 3 axioms there, or perhaps 4, oops, very low, or perhaps 4 if you include closure. And it's something of an amazement even to me now, and I've been working in groups for years and years and years. Even now I have to pinch myself and think that there is so much theory, so much rich algebraic insight, so much structure and so much to know about groups, when all of it, absolutely all of it, comes out of these 4 axioms here. Quite astonishing. Okay, I'm going to stop there. I'm going to illustrate all of these concepts with examples, and I'm going to show you how they work, but for the moment I just want to get the groundwork going and just make sure that we've got our axioms stated so we can refer back to them later. Okay, I'm going to stop there.